Hi everybody. So in this video, we're going to look at finding the nth roots of a complex number. So in example 1, we're asked to solve this equation, given our solutions in exponential form. And then we're going to show these solutions on an Argand diagram. So to start this question, we're going to convert this complex number into modulus argument form. That will give us our radius and the argument. And then we'll look at taking the cube root of both sides, and that will give us z. So the first thing we need to do is to sketch an Argand diagram. You can see we've got a real part of 4, so that will go about here, and an imaginary part of 4 root 3. So our complex number comes from the origin to the coordinates 4 and 4 root 3. And this is z cubed. So now we can work out the argument, which is the angle from a real axis to the complex number. We'll label this theta. So then we can work out theta by considering this right angled triangle. The tangent of the argument will be the opposite side, which is 4 root 3, over the adjacent side, 4. So theta will be the arctan of root 3, which gives us, in radians, pi over 3. So this is our argument. So we start on a real axis, and we rotate pi over 3 radians to get to this complex number. But we could also get to this line if we rotated another 2 pi, and then theta. Or we could rotate 4 pi and then theta. So we could write this argument as pi over 3 plus a multiple of 2 pi. And we can call that multiple k. So our argument becomes pi over 3 plus 2k pi. So for instance, if k was 1, we would rotate 2 pi, and then we'll add pi over 3. If k was 2, we would have 2 rotations, and then pi over 3. So we always land on this complex number. It also works if k is negative. If k was negative 1, it would be negative 2 pi, and then plus pi over 3. So it's really important that we understand that this is the argument of our complex number, okay? Pi over 3 plus 2k pi. Now we can work out our radius. This will be the square root of 4 squared plus 4 root 3 all squared. And when you work this out, we get the radius to be equal to 8. So now we can write the complex number z cubed in modulus argument form. The radius of 8 multiplied by cos of the argument, which is pi over 3 plus 2k pi, plus I times the sine of that same argument. And just to be clear, this k is the number of revolutions. So now to find z, we can take the cube root of both sides. And using De Moivre's theorem, this gives us z is the cube root of 8, so 2, multiplied by the cosine. Then we can divide this argument by 3. So we get pi over 9 plus 2k pi over 3. This is through De Moivre's theorem, plus the I sine of that same argument. Okay? So at this point, I find it really useful to simplify this addition. So if we've got pi over 9 plus, we can write this fraction with a common denominator, so 6k pi over 9, which gives us 6k pi plus pi over 9. And then we can substitute this argument into here. But I'm going to convert this now into exponential form. So z will equal 2e to the 6k pi plus pi over 9 times I. So at this point, we need to think about different values of k. When k is 0, we start on the real axis and we go straight to the z cubed. So when k equals 0, our solution will be z is equal to 2e. This term will become 0, so we'll just get pi over 9i. And then when k equals 1, we'll substitute 1 into here. This means we'll go 1 full rotation, and then we'll add theta. So z will equal 2e to the 7 pi over 9i. But now we have a problem. When we let k equals 2, we get 12 pi plus another 1, so 13 pi over 9, which means we've gone beyond our limits. So what we need to do is let k equal -1. So this means we're going to go around this way and then back by theta. So z will equal 2e. Substituting in -1, we get -6 pi plus 1 more. So -5 pi over 9i. And because we're looking at z cubed, there'll only be 3 solutions. Then to show them on an Argand diagram, well, we've got our fixed radius of 2 from the origin. We know this solution will be pi over I from a real axis. So this will go to here. We'll call this Z1. For our second solution, we'll have an argument of 7 pi over 9, which will be about here. We'll call this Z2. And then for our third solution, we'll have an argument of -5 pi over 9. So that will go to about here. We'll call that Z3. And then can you see that each of these solutions are separated by 2 pi over 3 radians? So another way we could have done this is we could have worked out Z1 and then add 2 pi over 3 to get to Z2. We could have subtracted 2 pi over 3 to get to Z3, okay? So we could either use different values of k, or we could plot the first solution on an Argand diagram and use this value to calculate the others. And we call this value omega. And this is 2 pi over n, where n is for power, so in this case n would be 3. Okay?